Okay, moving on. We're now in thermochemistry. So we're going to define energy. Energy is better as the force times the path length, our integral of F dot ds. But energy is defined now as the capacity to do work. And we've learned about the joule dimensionality before, kilogram meter squared per second squared. So it's a Newton meter. And Newton is mass times acceleration. So kilogram acceleration is second derivative. Um, so it's meter over second squared for acceleration, and then a Newton meter is the meter squared. So if you're wondering, that's how I remember it at least. Okay, so energy, and we've covered this in chapter one, what definition of energy was, and we have kinetic and potential energy. And I'm going to start off with the law of conservation of energy. The law of conservation of energy is that energy is not created or destroyed. And well, let me zoom in this picture here. This is most of the thermochemistry right here, is the system. So picking the system, and then energy flow into the system is the positive direction, energy flow out of the system is the negative direction. Figuring out what the system is, and that is the majority, at least that I find, that is where most of the mistakes are, and this is seems to be the hardest thing that students um, have with this. So a couple other things. Kinetic energy is 1/2 times mass times velocity squared. Cover that in gas laws. So let's go in and we'll talk about the first law of thermodynamics. The first law of thermodynamics is the change in internal energy of the system, delta E, is equal to the work plus the heat flow. So W is work, Q is the heat flow. So let's see how you're doing this. If the change in internal energy is 50 joules and work done is 20 joules, what is the heat flow? Heat flow is 30. So hopefully this is a little easier for you. But okay, let's go on and talk about some other things. So units for heat, we frequently use joules, also used often as calories. So a nutritional calorie, if you notice, it's capital C. The capital C means kcal, kilocalorie. So a calorie is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. A nutritional calorie is the amount of energy it takes to raise 1 kilogram of water 1 degree Celsius. So that's the heat flow there. And there's about 4.18 joules in a calorie. Other units, there's BTU, British thermal unit. That's the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. So BTU is much larger than a joule or a calorie. I don't know what the conversion ratio is. Sometimes you also see ton, TONNE. That is 2,000 BTUs. So if you wonder what that is, air conditioner units frequently are use that term for energy flow. Okay, so now moving on, heat capacity. So heat capacity here, well, I should say heat flow, Q, heat flow. Heat flow is equal to heat capacity times change in temperature, but more frequently you see the intrinsic term specific heat capacity. So the mass times the specific heat capacity times change in temperature. So think of it kind of like density versus mass. So it's a similar idea. But let's do some problems and you'll see what I mean by that. Okay, so temperature change and heat capacity. Pennies used to be made of copper. Now they're copper coated zinc, but hey. So suppose you find a penny, you throw it in the snow, it's at -8 degrees Celsius, and then as you put it in your hand, it goes from 8 degrees Celsius to 37 degrees Celsius. So one thing about this, the hand temperature is usually not 37 degrees Celsius, usually around 33 to 35-ish range. But hey, well, let's just go and do the problem. We'll talk about what's wrong with it. So use this equation here. Heat flow Q is mass times specific heat capacity times change temperature. So we would just apply this equation. The mass is 3.10 grams of copper. That's copper times specific heat capacity of copper. What is the specific heat capacity of copper? It is 0.385 joules per gram degrees Celsius. Time to change of temperature. Temperature is always delta T is the final minus the initial. So the final is 37 minus a minus 8 degrees Celsius. So let's look at the units. Degrees Celsius cancel, grams cancel, and we're going to be left with joules. And the answer is, where is the answer? 53.7 joules. 53.7 joules. Okay. So a couple of things with heat capacity. When you look things up, you might see different units. One of the units you'll see, it might say 0.385 joules per gram Kelvin. Okay, so unit-wise, for units only, degrees Celsius equals a Kelvin. So you can cross-cancel and multiply degrees Celsius and kelvins if they appear. The size of the unit, so a degree Celsius step is the same thing as a Kelvin step. The magnitude of them are different though. So that's one thing. If you are dealing with addition and subtraction, you cannot do them interchangeably. But when it comes to unit cancellations, Celsius and Kelvin are the same. So if you do see units in Kelvin, you are free to use them as well. Okay, so this one I wrote some things down because there's so much to write down. Thermal energy transfer. This is where you have the system, and it's a problem that I always think about, where is the energy flowing and this kind of thing. Okay, but let's go to the problem. 32.5 gram cube of aluminum initially at 45.8 degrees Celsius, submerged in 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Assume that no other heat is lost. Okay, so this is what we know. That we have 105.3 grams of water at 15.4 degrees Celsius, and we have 32.5 grams of aluminum at 45.8 degrees Celsius. And we throw the aluminum cube into the water, as shown there, and then the heat flow leaves the aluminum. So that's part of it. I think about where the heat flow is going. Heat always flows from hot to cold. So it depends on the system. The system leaving, so the energy leaving the system, the aluminum block, is negative. So remember, system energy leaving the system is negative. The water system, the energy flow there is positive. The water is going to heat up. So, as written here, the heat flow of the aluminum, the opposite, the heat leaving the aluminum is going to be the heat absorbed by the water. So, and delta T is final minus initial. So the Q is M, specific heat capacity, delta T. So minus mass of the aluminum, heat capacity of the aluminum, times the quantity final temperature minus the initial temperature, equals the mass of the water, the heat capacity of the water, final temperature minus the initial temperature. So the next thing we're going to do is we're going to solve for the final temperature. So you basically go and you rearrange everything to solve for the final temperature, and I've done that there, and I did this before because it's just writing all this stuff down is a little mind-boggling of sorts. Then you write it all down, and you notice put in the values. And then when you set everything up and you put in the values, you actually get the final temperature, TF equals 17.3 degrees Celsius. But it is this one, I mean, it's an easy enough problem. This is the algebra is kind of tough to do that. So anyways, So recap with this one. The way you solve this problem is think about the heat flow. And heat flow is leaving the aluminum and is being absorbed by the water. So you write out the Q equals mc delta T for both. Rearrange the equation to account for the final temperature, and then put in the numbers. So do the algebra, put in the numbers, and the final answer. Now, does the final answer make sense? So we started off at aluminum at 46 degrees Celsius and water at 15 degrees Celsius. And the final temperature is 17 degrees. So it's just warm the water a little bit. Does this make sense? Well, there is 3 times as much water, and if you look at the heat capacity of water is 4.18, and the aluminum is 0.902. So means that water can absorb a lot of energy. So uh, because of that, so that makes sense. And it's above. It's not like it's cooling off. It's actually getting warmer. So actually, I think this result makes sense. So that's the check. Okay. So let's go on and talk about work. So we've already talked about heat flow. Let's talk about work. So to inflate a balloon, you must do pressure volume work on the surroundings. If you inflate the balloon from a volume of 0.1 liters to 1.85 liters against an internal pressure of 1 atmosphere, how much work is done in joules? So let's see here. The work is P delta V, and it's kind of hard to say where the direction of the heat flow is, or I'm sorry, energy flow. So the work is done on the surroundings. So that means that it's being done, it's leaving the system. So the energy flow should be negative. And work is P delta V. So work then is equal to minus 1 atmosphere of pressure and times P delta V. So final 1.85 minus 0.1. So this is equal to negative 1.75 liter atmospheres. So that's the volume of 1 liter. And what the heck is a liter atmosphere? So to solve this, to get the conversion, I always think of in terms of the two ratios of R. So we want joules per liter atmosphere. So we're going to do, to get the answer in joules, 1 is 1.75 liter atmospheres times, and we want it in joules, so we have 8.314 joules per mole Kelvin all over 0.08206 liter atmosphere mole Kelvin. And these cancel, liter atmospheres cancel, and we're left with joules. So that times 8 divided by that would be negative 177 joules. Okay, so that's how you solve that kind of problem there. So that's the work, P delta V. And I guess I should talk a little about the first law. Now that we've gone through some of these things, I should go back and talk about the first law. One thing about this, I don't know what math level you're at right now, but if you go on, I don't know if it's Calc 3 or Calc 4 in the UH system. I didn't, when I took calculus, it was my Calc 3 and 4 were the same class. But when you go on and study more math, you'll learn about something called exact differentials. That is, if you have a function and if the partial differentiation of x with respect to y equals the y to the x, this is known as an exact differential, and then this function is called a mother function, and it's path independent. So that means that no matter where you go, it doesn't matter what path you take, and you will get the same answer. So uh, if this is not true, then the function is path dependent. So state functions, so like E, internal energy, state functions are path independent. Work and heat, though, these are path dependent. So, for instance, the amount of energy that you get when you burn a gallon of gasoline is the same. It doesn't matter, well, if you burn it, if you throw it into a car, you usually get about 20% of it in work. So let's say we have energy equivalent of 1,000 joules of gasoline. I can take that 1,000 joules of gasoline, I can burn it, and then it just turns into heat, no work. Okay, so then I can take that 1,000 joules of gasoline equivalent and throw it into a car, and its cars are usually about 20% efficient, so I can get about 200 joules of work and 800 joules of heat out of it. I could throw it into a fuel cell car, and I can get 600 joules of work and 400 joules of heat out of it. So, but the thing is the amount of gas that I'm burning is going to be the same, but the amount of work and heat that I get out of it is different. So that's what I mean by path dependent and path independent. So the path dependent, path independent things are going to be important later. And I mentioned the car because if you look at this example, pressure, volume, work, that's how your car works. Either if it's gas or diesel, it's the same thing. You have an like internal combustion engine. The internal combustion pushes the expansion of the gas, pushes pistons up and down in your engine. That's where the engine gets its energy from. Is the exploding gasoline which causes the pressure, the P delta V. That is where the energy comes from. If you're wondering where the work comes from in your car. Okay. Moving on, it's a bomb calorimeter. So a bomb calorimeter, what is a bomb calorimeter? It is a very insulated piece of equipment. And in that, you burn things. So part of this is so I mentioned state function. The other part of it, there's U.S. laws. So there's a series of laws called the Code of Federal Regulations, and it is a huge amount of laws. There are so many of Code of Federal Regulations, and they describe everything. Well, not everything, but they have ways of measuring things. A lot of them are scientific and descriptive in that regards, and they're in order to say what the caloric content of food is. You burn the food or whatever it is, your additive, any bomb calorimeter, to figure out the calories. And the idea is, well, if I burn in a bomb calorimeter as path independent, the internal energy is path independent, then that's the same energy that I get whenever I burn in the cells. And the question is our body really going to burn sucralose? And I don't think it really can. I might be mistaken on that, but I don't think that we really actually do burn the sweeteners. I think we just burn the sugar. But I mean, but that's the idea behind this bomb calorimeter. Bomb calorimeter, what it is, it's like a really thick. You have like a really thick walled vessel, and in it you have oxygen going in, and then you have a chamber where you put your sample, and you burn it in that sample, and you burn that in the chamber, and then you look at to see how much the temperature increases for this bomb calorimeter, and from that that is the change in temperature of that. You can figure out the heat of that, and then the heat of the system, which we'll do in this example. Okay, well, this is sucrose. This our body can burn this, so this is true. Sucrose our body can burn. But let's say we have 1.01 grams of sucrose, and we burn in a bomb calorimeter. The temperature rises from 24.92 to 28.33. Find the heat of reaction, or delta E reaction, change internal energy of the reaction for the combustion of sucrose in kilojoules per mole sucrose. Heat capacity for bomb calorimeter is 4.9 kilojoules per degree Celsius. Okay, so remember I had Q is M CS delta T, and I also had is C delta T. We're using this equation. So that's the equation we're going to do. And so actually, before I start this, I should talk about heat flow. In my mind, heat flow, the sucrose is burning and the temperature of the bomb calorimeter goes up. So that means that it's negative. So the sucrose, the energy is leaving the system. So our delta E for sucrose is negative. So let's keep that in mind as we're going through the equations. I have a kind of a right-brained approach to everything here. I always think I hate it when I miss that negative sign. So I'm always, where's the negative sign? Where's the heat flow going? Okay, so that means our heat is C delta T, which is equal to 4.9 kilojoules per degree Celsius times delta T final, 28.33 minus 24.92 degrees Celsius. And our heat flow here for that is, it's going to be 16.7 kilojoules. Now let me think about the energy flow. The energy flow for the sucrose, the Q is, that's a Q. The heat flow for the sucrose is negative, so it's minus 16.7 kilojoules. And that's because of what I mentioned before. The temperature of the bomb calorimeter is going up. Now, the next part is we have to figure out, so this is 16, so we have, let's see here, we have minus 16.7 kilojoules, and this is per 1.01 grams of sucrose. So then we have, so let's see here, 342 grams of sucrose per mole of sucrose. I have this one memorized, to be honest with you. Glucose is 180 and sucrose is 342. I always remember that. And then this will tell us the answer in kilojoules per mole. So we're trying to convert that. We have the ratio here that minus 16.7 kilojoules of heat is evolved in 1.01 grams of sucrose. So we multiply by the molecular mass, and doing so, we get, what do we get? We get minus 5.66 times 10 to the third kilojoules. That's a 5. Sometimes my 5s are sloppy. Kilojoules per mole sucrose. Okay, and this is your answer. There, like that. Okay, recap on this one, and this is where heat flow is important. And so we have a bomb calorimeter, and we're burning sucrose in the bomb calorimeter. The bomb calorimeter's temperature goes up, so which means that heat is leaving the system. So the system, the reaction is exothermic. It's generating heat. So when we look at the heat flow, we put that in the negative sign, and we calculate the heat flow to be 16.7 kilojoules. And we give it a negative sign because it's the sucrose is pushing out heat, so that means negative heat flow. And then this is 16.7 for 1.01 grams of sucrose, so multiply by the molecular mass to get the answer in kilojoules per mole. Okay, so why don't you try? 18 grams of glucose burns in a bomb calorimeter. 1 kilogram of water raises from 10 degrees Celsius to 70 degrees Celsius. What is the delta E reaction? So why don't you give it a try? Okay, so the heat flow is negative, so you can discount B and D. And we have 1 kilogram of water, so we have our heat flow is 1,000 times 4.18 times 70 minus 10, and so that's just throwing in our heads. This is about so that's 60. This is 250 kilojoules, and 18 grams per mole, so 250 kilojoules divided by 18 grams of glucose times 180 grams of glucose to mole glucose. And I also mentioned the negative direction for the heat flow. Then this is minus 2,500 kilojoules per mole. So, like so. All right, that's how you solve that one. And I've been kind of talking about this already, but now here is some of my drawings. So think of an exoskeleton. So like insects have exoskeletons. We have endoskeletons. We have our bones on the inside. Insects have their bones on the outside. So exothermic means heat leaves the system. So that's like a fire. I'm trying to show you that that's my picture of a fire, and heat flow is that way. That's our negative. Exo is out. Exo is out. Energy is negative. Endothermic, like your bones, endoskeletons on the inside. Heat flow goes in. That's supposed to be a snowman. I don't know if you've ever, and this is Hawaii. I used to make snowmen when I was a kid. Uh, it was a fun thing to do, especially when the snow was kind of not powdery, but you kind of wet. You could really make a pretty awesome snowman there. But anyways, energy flow is positive for endothermic, so it goes into the system. So there's some of my drawing. Okay, so like I said, later on when you learn more math, you'll learn about how it is if you go the route and you take Calc 3 and 4, you can learn about the exact differentials and how that works in path independent nature. So things that are path independent, internal energy is E is path independent. H enthalpy, which we'll talk now. G Gibbs free energy is another one, and S entropy. There's others too. Helmholtz free energy, for instance, is one. Work and heat are not. Q and W are not. But okay, so this is a thermoderivation, and we are having a new term. The term is H enthalpy is being defined as energy plus pressure times volume. So we're going to do the change in enthalpy is and under a constant pressure. So if you know your calculus, the derivative of pressure times volume is going to be P prime V plus V prime P, like that. And if pressure is constant, there is no change in pressure. So it's just the derivative or of the volume. So sorry if I'm using calculus terms in here. Calculus is not a prerequisite for this class, but I'm letting you know that calculus is used to derive these equations. You just have to know how to use them if you've never had calculus before. So that's how you derive this step there, is by using the multiplication rule of derivation. And then if you apply the first law, so the first law is heat flow plus work, so we include that. So taking this term, including the first, applying the first law of thermo, you get the, under constant pressure, the enthalpy is the heat flow. And quite frequently, enthalpy is referred to as the heat of reaction because of that. Okay, so, and the same idea, uh, is that positive delta H, just like delta E, means energy is flowing in the system. Negative means it's going out of the system. And positive delta H means endothermic. Negative delta H means exothermic. So endothermic is going to be cold if you touch it. Exothermic is going to be hot when you touch it. Okay, and we are done for there, and we will move on in the next lecture.